Okay, so today what we're going to do is wrap up our discussion of radiation. That involves kind of cleaning up a few points on the gray body radiation exchange. And then we're going to talk about semi-gray radiation exchange. Semi-gray was where we no longer treat the surface as having a single emissivity as a function of wavelength. Now it's broken into increments based on its wavelength. So just to wrap up, we went through this last part really quickly last time. We were talking about a three-surface problem and trying to come up with a model for how radiation flows in this three-surface problem. And we decided that, okay, we can have the same kind of triangle, right? The same three-surface network that we had with just black surfaces. But the difference here is that this radiosity is actually what sees the other surfaces, right? Now, if we have a resistance or we have an emissivity, that's not one, this black body emissive power is not what is directly seeing or directly interacting with these other nodes, right? It's the radiosity. The radiosity is the important part there. And we said that if emissivity is equal to 1, then that essentially short circuits this resistance up here, the surface resistance. And then black body is equal to radiosity. And just to think about that, because we kind of glossed over it, why is it the case that if it's 1, that happens? So let's look at here. So we'd have 1 minus 1 over AI times 1, right? So the resistance here would go to 0, right? And if the resistance goes to 0, we look down, let's say, at this equation down here, we're dividing by 0, yes, but not if we take the resistance and bring it over to the other side and multiply Q times that resistance. So then that left-hand side becomes 0, which just says EBI is equal to JI. Right? That's all we're doing if we say that resistance is 0. Okay, so that was one point I wanted to make. The other point I wanted to make about this was the system of equations that we came up with. If you remember, originally when we had just black surfaces, we had n equations. So like we did an energy balance on each of the emissive power nodes. That gives you n equations. And then we had to come up with n more boundary conditions, right? We didn't know the emissive powers and we didn't know the heat transfers, Q dot. So when we introduce radiosity, now we have this additional set of variables. We have the EBs we don't know, we have the Js we don't know, and we have the Qs we don't know. So we had to do energy balance on, let's see, so we had to do an energy balance on, first of all, this surface resistance, right? So this one here, that gives us an equation. That's a new set of equations compared to the black body. And then we have to do an energy balance on each radiosity node. And now instead of it being EBs in here, right, this is Js instead of EBs. Right? So that's the only difference from the black body approach. And then in addition to this, we need n more boundary conditions. We still have to specify, do we know the temperature? Do we know the heat transfer rate or whatever? We still have to specify n things about the surfaces. Okay, and then last thing was I made kind of I think a confusing statement, but what I had said, if we have heat flow here, so let's look at Q dot 2, we have heat flow going from EB2 to J2. And I said it's kind of this like virtual like heat transfer. What I meant to say was it's an actual heat transfer, but there's no like physical space between these two nodes, right? There's no physical space between EB and J, right? It's heat is actually flowing across the surface. Q dot 2 is maybe losing or gaining heat, but there's no physical space. It's just the kind of a conceptual resistance associated with emissivity not being equal to 1. Okay, so, all right, so that just kind of wraps up the, I think, discussion from last time. Any questions on that or confusion still? Okay. Okay, so let's move on to an example here. We have an example for diffuse gray surfaces. Let's revisit this same system that we had before. This is like a pipe that's containing liquid nitrogen. There's an evacuated region in here. We're trying to keep this thing cold, so we have this radiation radiation shield here. And then we're specifying some things about the surfaces. So we said, one, that surface 2 is insulated. Surface 4 is at a specified temperature. Surface 1 is at a specified temperature, and surface 3 is. So we have, 1, 2, 3, 4 things we're saying about this problem. All right. So that's all the same as last time. What we're changing now is that we're going to introduce emissivities, right? We're going to make the surfaces not black anymore. I guess I didn't write out what the emissivities are, but I have them in the ease file. So let's, just before we jump over to the ease, let's look at what we have. We are doing an energy balance on each surface, right? This is the surface resistance for each surface, and then we have an energy balance on each radiosity node. So we're doing that to come up with 2 N equations. So let's look at how we can actually implement something like this in ease. Let's see, this one, gray surface example, okay. So this should look really similar to the example we went over last time, or the last time we looked at this problem. We start off by specifying our geometry, our areas, that's all the same. Now, instead of every emissivity being equal to 1, we're going to come in here and specify an emissivity for each surface. Right, so we have now this vector or array of emissivities that's going to make this a little bit more interesting. We still have our view factors. They're all the same here. Nothing has changed on the view factors. And then we have our energy balance on each surface, right? So here is our, let's see, we're taking the Q dot for each surface. It's going to be the area times the view factor times the difference in potential. So before we had said these were EBs. It's a little hard to see. Can you guys all see that okay? You're less blind than I am. All right, so we have all the EB, we had EBs, now it's just J's, right? So JI to JJ for subscript J from 1 to 4, and then we duplicate that 4 times, right? So we're doing that energy balance for each surface. That's the same, except we're using J's. Now we also have to add this surface resistance, right? So this is a new set of equations that we're adding. Our surface resistance EB to J. So this is going to be associated with just with node I, right? There is no interaction of surface J in this set of equations. And then what? So then we are saying EB is related to temperature in this way, so that we can specify temperatures. And then we do that. Here's our specified temperature, specified heat transfer, and the other 2. So this should be able to solve. Now, we solve this. Let's see. So we'll look in the arrays table. So what we're seeing in this problem is something you'll probably see in the homework. You have this view factor table. That's basically as far as you're going on the homework, right? So computing view factors. But now we have black body emissive power. We have radiosity, and then we have the temperature of the surfaces. So you can see what's happening here. Everything is solving for the degree of freedom that it has. We are solving for temperature here by specifying the heat transfer rate. We're calculating heat transfer where we're solving for temperature. And in the end, we see that that surface 1, so what's surface 1? So surface 1 is this cold tube in here. So it should be gaining heat. In fact, we see that surface 1 is gaining 1.4 watts. And where is that coming from? Well, it's coming from surface 4, right? That radiation shield that's out there. So yeah, I mean, it kind of makes sense, but it's really a pretty straightforward method. You just are going through, keeping track of view factors, and then kind of go through this just process of computing each energy balance on each node. Okay, any questions on this example? Nope. Good. All right. One other thing we can do on this example, let's see if I can do this on the fly. So one thing that you commonly are going to find is that you don't necessarily specify the temperature in a problem like this. You know something about the heat transfer coefficient on the surface instead of the temperature of the surface. So let's say on, surface 4, let's look back here at our example. So on surface 4, we don't actually know that the surface is at 300 degrees Kelvin. we want to model this using a heat transfer coefficient and convection instead. So this is pretty easy to do. What we come in here and want to do is we've specified 300 here. So let's actually comment that out. And then we're going to introduce a little model for this surface instead. So we're going to say our H bar is 5. T infinity is now 300. Right? So the ambient temperature is 300. And we have now our rate equation. So the rate equation is just convection area times the temperature difference, T infinity to T4. We don't know T4. And we're also solving for Q dot, but we're just bringing in this extra rate equation to help us solve for T4, right? So this is actually the way you're going to experience a lot of problems in kind of real life. Okay, so good, it worked. So here we're solving for T4, and instead of 300, that surface is actually at 276. So it's still possible. I guess the point of this is to show it's still possible to bring in the other rate equations that we have that aren't just radiation, or you can incorporate other aspects of heat transfer into these problems. You just have to be careful about how it involves the boundary condition.